Hi everyone, my name is Andre and I'll be your host today. I'd like to welcome you to our live show called Diving into the Abyss. I'd also like to know where you're watching us from, so feel free to drop in your comments where you're watching us. During the talks, please feel free to drop your feedback, any questions or any comments that you might have on the talks, and we'll discuss this later on the Q&A. So with us today, I'll move on to introduce our first speaker, Dr. Carolin Villforth from the University of Bath, Department of Physics. Carolin will be talking about what happens when you feed a black hole. Without further ado, Carolin, the screen is yours.
Thank you, Andre, and welcome everyone to this Pint of Science virtually. So this evening, I'll be talking about supermassive black holes, how to feed them, and more importantly, what happens when you do feed them. So before we can get started with talking about how supermassive black holes affect their surrounding, let's first figure out where we might be able to find them. And where we find supermassive black holes is within galaxies. So here you see kind of a beautiful picture of different galaxies. So these are kind of these blobs. And what those galaxies are basically large collections of stars. So something like our own sun, and gas and dust. And they're basically bound together into these massive systems here. And those are galaxies. And until a few decades ago, we kind of thought that this is really what was outside our own galaxies. What we had is other galaxies made up of stars. But it turns out that what we find within these galaxies is supermassive black holes. And where we find them is in the very, very center of those galaxies. So we now know that supermassive black holes basically all have galaxies basically all have supermassive black holes at their very centers. And what are their properties? Well, these supermassive black holes have masses that range from maybe 1 million to a few billion solar masses. So let's say that again to be impressed by it. These supermassive black holes have masses 1 million to 1 billion times the mass of our own sun. So that's incredibly massive. And we should also quickly think about what we actually mean by a black hole. And by a black hole, I basically mean an object that is extremely compact. So black holes are the most compact objects you could think of. So if we think of our own sun, and we would compress that mass down into a black hole, the size of it would be about 3 kilometers, so really quite small. And if we took our own Earth and compressed it into a black hole, it'd be about the size of this kind of pin here. So this is a sewing pin, so that would be about the size of the Earth if we compressed it into a black hole. So incredibly compact. And this will actually play a big role later on in this talk. So these are black hole centers of galaxies. Now, if we think about the fact how extremely massive they are, we might think, well, if they're that massive, they must have a really fundamental impact on the galaxy just through their gravity. So let's think about that one first. Let's think about the question, does the supermassive black hole matter to its galaxy? So this is another picture of a galaxy here. And so let's think about the fact, like, will the supermassive black hole that sits in the very center here have a strong impact through its gravity on the galaxy around it? So let's repeat that. This black hole will have a mass of 1 million to 1 billion times the mass of the sun. We also learned that it's extremely, extremely compact. And more importantly, it's much more compact than the galaxy. So the galaxy size will be a few thousand, maybe 10,000 light years. So it's large. But, and so the black hole itself will be the most massive object within this galaxy, because all the other objects will be about the mass of the sun itself. But the fact is, because this galaxy is so large, it actually contains a lot of matter. So if we sum up all the matter within the galaxy, the black hole is only a tiny, tiny part of that. And due to that, the black hole, in terms of its gravitational influence, actually only matters in the very, very center. So even though it's very massive, sorry, something just drove by and had a really weird sound. So even though individually it's very, very massive, overall it doesn't have a large impact. It basically drowns in the large sea of mass within the galaxy. I really have no idea what that is. So overall, it doesn't matter. So it only dominates gravitational potential in the very, very center. All right. So does the supermassive black hole matter to its galaxy? In terms of the gravity, actually, surprisingly, no, not really. So unless you are in the very, very center, you kind of don't really feel the black hole because there's the sea of matter that washes it out. Okay, so in that case, can we just forget about supermassive black holes? Well, not really, because let's think about the fact what actually happens when you get matter towards the very center. So what happens if there's matter going in towards the very center of this galaxy, so in this region where it really dominates? And what happens at that point is that we can actually start to feed the black hole. So the black hole is very, very massive. And if we actually get matter towards this very, very central region, it can start to feed the black hole. And this is a picture of a galaxy where this is in fact happening. So this is my favorite galaxy, Carolin 231. It's a beautiful galaxy. It has everything you'd want in a galaxy. And what you see here in the very, very center is this very bright spot here. And this is in fact a black hole that's currently feeding. And this central region here around the black hole is extremely, extremely luminous. So while it isn't quite clear from this image, the central region here is brighter than that entire galaxy. And this is a feeding black hole. So what's happening here? We kind of learned that in terms of gravity, the black hole gets washed out from all the mass within the galaxy. But what happens here while it's feeding? Let's think about that. So what happens if you feed a black hole is basically, if you have a gas cloud that will come in, it will start to kind of rotate around the black hole, and it would start to form this kind of an accretion disk, we call it. So it's kind of a disky structure around it. And within that, the matter will start to in-spiral, and this has very high densities, and it will heat to very high temperature. And this very high temperature gas will basically start glowing. So it will start radiating thermally. So you can see it, right? The same way that you could see, I don't know, hot coals. So it's thermal radiation. So gas inflowing, heats up to high temperatures, starts radiating because it's quite hot. And this is what we can see centrally here. And that's a feeding black hole. So that's already quite exciting. But let's think about the fact that it's quite surprising that this black hole, which in terms of its mass didn't really seem to matter, suddenly, if we're feeding it, is brighter the entire galaxy. So what's happening here? And for that, I would like to make you think about the gravitational potential of the black hole. This will sound a bit like weird and physicsy, but I hope I'll have a good explanation for it. So I have an explanation here. So that's a supermassive black hole in the center. And then this red line here is the gravitational potential of the black hole. And basically here's the distance from the black hole towards the right. I've also drawn some mountains here that I'll explain in a second. So the gravitational potential, we can also call that the gravitational potential well. So we can basically think about the black hole sitting in a very, very deep valley energetically. So the black hole is in this very, very deep valley here, and there's basically high mountains towards the side of it. And the way we can interpret that is saying, well, if I'm somehow trapped near this black hole and I would like to escape this gravitational potential of the black hole, what I need to do is I basically need to climb up this gravitational potential. So here I've drawn this little figure, and this little figure has to climb up here. But to do so, it has to basically use up energy to get out of this potential well. And because the gravitational potential has to show that has the shape that is shown here in the center here, this is basically a very, very steep one here. So basically, you have to spend a lot of energy for each step to get out of this gravitational potential. Whereas further out, this starts to be rather shallow, so we can really think about ourselves like walking up this slope. So up there, we can just walk along, and each step is not as exhausting. So this was what would happen if I wanted to escape the black hole. I'd have to use energy to do so. But from the accretion disk, what we actually have is the opposite. There, the matter is going inwards. So what then happens when the matter is going inwards? Well, basically, rather than climbing outwards, we are now falling down this slope towards the black hole. And if we turn the situation around, previously we had to use up energies to try to escape the black hole. In this case, we're basically kind of throwing this energy away as we're falling into the black hole. And it's in fact this situation here, so this kind of falling down this potential well, that is creating all this radiation. All this radiation in the accretion disk and is heating it. And okay, but so far I haven't really used a lot of properties of the black hole. So why is the black hole special here? And the black hole here is special because it's so extremely compact. So as we said before here, basically, where we are far, the gravitational potential, only some energy is released at radiation. So in terms of like how much energy I'm actually throwing away and radiating, there's not a lot of it. Whereas there's a lot of it in the center because it's so incredibly steep. So each step I'm really falling far down here. Okay, so lots of energy in the center, a lot of energy out. But if we think about a black hole, what we said, it's very, very compact. So if it wasn't that compact, if it was a normal kind of object, then it'd be very, very large, and we basically wouldn't have access to this part of the gravitational potential in the center here, where we are radiating a lot of energy away. So it's this compactness itself that really causes a lot of energy to be radiated. So this kind of leads us to the fact that if we now ask again, well, does the supermassive black hole matter to its galaxy? And we just think about the amount of radiation it creates, the answer is actually yes, surprisingly enough. So this supermassive black hole here is brighter than the entire galaxy. And it is so only because we can get the material very, very close to this compact object to create all this radiation. So yes. So, and this is a very exciting finding, actually, if we think about it, because the black hole itself, again, the mass is very, very small. But once we start to feed it, we can create a lot of radiation. And this radiation can start to interact with the galaxy and can really have a massive impact on how this galaxy might evolve in the future. Right, and so hopefully I convinced you that supermassive black holes play a really exciting part in galaxies. And I'll give the screen back to Andre, I believe. And I'll see you later in the discussion round for questions and answers. Goodbye.
Thank you very much, Carolin. That was really interesting indeed. And I imagine that even though you made it look really easy and easy to explain, the physics behind it, it's quite complicated.
Yeah, I try to tone it down a bit.
Thank you for that. I'm pretty sure that our audience is also thanking you. So I'd like to remember everyone to drop in your questions and any comments that you might have for Carolin, and we'll discuss this later in the Q&A session. Now, in between the two talks, we have also prepared an interactive activity where everyone can participate. So basically, this is an emoji quiz. And even though you might have not participated in one, we have prepared a couple of examples so that everyone knows how it works. So we'll be giving you categories, and for example, on the first one, it's the category is films and TV shows, and we basically have 2 angels and 2 demons. So the name of the film is Angels and Demons. On the second one, for example, a country, it's not as straightforward as in the first one, but you'll have to remember which country reminds you of pizza, pasta, and the chef. And I think it's quite easy for everyone to say Italy, and everyone will agree with that. Now, moving on to the first category, we'll have artists and bands. And please feel free to drop your comments. Even if you don't think it's right, feel free to do it. And feel free to discuss your ideas with the audience so that we can discuss and talk about it. Now, for example, the first one, I can tell you a name of a song of this band, which is Sweet Child O' Mine. I'll move on to the second band, for example. A song really famous from them is Pump It Harder. So, for example, in the first one, we'll have, this can be called pistols, or alternatively, can also be called another name. Yeah, we've got the first answer for number 2, which is Black Eyed Peas. Well done for that. Also for the first one, Guns N' Roses. So 2 Guns and 2 Roses. Yeah, well done. Moving on to the third one, for example, we have an arrow to the left. These on emojis can be read as left or something else. And the second emoji can be quite confusing, I can imagine, but this can also be called a road. Fifth one is Queen indeed. I was not able to read what was a long reply to 3 and 4. So if you wouldn't mind to give shorter answers to 3 and 4, that would be great. So for example, fourth, you have girls at the end and then something at the beginning. I can give you some songs from them, and this will be Wanna Be or Viva Forever. And some examples on number 3 will have I Want It That Way or Everybody. Okay, so if, for example, on the fourth one, I tell you this is spicy, I think that's a great help to tell you what's coming up. It's quite an old band from 2000s, if I can remember well. Yes, that's correct, Spice Girls. Thank you for that. And yeah, I can see a right answer for 3 as well, Backstreet Boys. I think you got it, guys. Well done on that. And here you have the answers for that. Well done, everyone. Thank you. Now, moving on to the next category, we'll have films and TV shows. So I'll also give you a few tips if you don't get into them. For example, the first one is quite recent TV show that everyone's been talking about the last couple of years. It has quite some seasons, 7 seasons, 8 seasons. There's a lot of deaths in it. People trying to conquer the kingdom. You can see dragons in there. It's quite famous, actually. A lot of criticism about the last season. Yep, that's correct. 6 is Game of Thrones indeed. Thank you very much. Yeah, that's it. For the 7th, yeah, well done on the 8th as well. That's correct. E.T. with a bike, a phone, calling home. That's E.T. Well done. And the 7th one, it's Apollo 13 indeed. Trip to the moon. Thank you. Yeah. Now the 9th one. The first emoji is the shape of the country. I can also see a nice answer for the 10th. It is indeed Planet of the Apes. Yep, well done. Now the 9th, it's about, let's start with the first emoji. It's the shape of a country. So an Asian country which dropped some bombs in another country where you have the flag. And this was in a dock area, let's call it that way. It's quite a well-known film. If you haven't watched it, please do. It's a good one, and I bet you'll have some fun. Yeah, we've got the right answer, Pearl Harbor. Yeah, thank you for that. Well done. And then again, we have the right answers for all of them. Thank you. Moving on to our final category, we have countries. Some of these are quite intuitive. So quite straightforward. Others, you might have to think on the words that are related to each emoji and form a word with those emojis. So on the 12th one, we got the right answer for the 12th. Indeed, we've got an ice and land, so it forms the word Iceland. We've also got the word for the 11th, which is O man. We've got an O and a man. And you can draw, indeed 15 is Thailand, so you've got a Thai and a land. That's the one. We've got 16th as well, Andorra. Well done. We've got and, door, and hey. 13 is indeed Madagascar. Thank you for that. You've got mad, a, gas, and car, which forms Madagascar. 17, yes, it is indeed Austria. So we've got, how do you call Australia? The flag, it's Aus, and then you've got a tree and a, which forms Austria. And I think we are only missing 14th. Yeah, it is indeed Panama. Well done. That is a pen, an A, and mother, which is Panama. Oh, that's how you can call your mother as mom. Thank you everyone for participating. Yeah, this is it, and these are the right answers indeed. Thank you for discussing it. Now we are moving into our second talk of the day. We'll have Dr. Philippe Blondel, also from the University of Bath, Department of Physics. And Philippe will be talking about exploring the world with physics. Philippe, to you.
Okay, thank you very much. And yes, I'm going to talk about physics as well, using similar types of techniques, looking at waves, propagation of waves, and exploring the world around us from the deep sea to outer space. When we explore the deep sea, we use sonars like dolphins. The toy dolphin on the right is using sonar. They have been doing it for thousands and thousands of years and much better than humans. We only started less than a century ago. And we can transmit waves. We look at how far the waves propagate from the echoes when they come back to us and how they are transformed by the seabed around us. So that enables us to go to the bottom of the ocean. Even if we have kilometers of water, we can go back to the bottom of the ocean, get information, and get maps of the seabed. These maps are very useful. For example, these are maps that I have done with my colleague Maria Cristina Prampolini from Italy when she was in Bath. And we looked at geohazards around Malta. Geohazards are a good example of how sea level rise and coastal erosion can change landscapes. We saw an example in the news today with Darwin's Arch in Galapagos that collapsed due to coastal erosion. What we can do is look at all the seabed around the islands of Malta and find out where the risks are. So reducing analysis times by using software and analysis of the topography, and increasing the confidence in how we use the data. We have been able to map the oceans. For example, I have worked on mid-ocean ridges and discovering black smokers. They are places where hot water comes at temperatures of 300 degrees, very hot in the deep ocean. You can see a deep sea vehicle, Alvin, there, which is the size of a pickup truck. So you can see how big some of these black smokers can be. Very often, they're associated to new ecosystems and life based on chemiosynthesis. The sonar is essential to discover exactly where they are, and we have used it to prepare diving surveys where biologists, chemists, oceanographers, geologists can explore all these different complex ecosystems. What we can do as well is look at marine renewable energy. We have different types of marine renewable energies. For example, we can have a wave energy converter that use the movements of the waves to generate energy. And we have tidal turbines, which use the tides of the currents. They're a bit like wind turbines, so they have blades moving around. And the big question was, what happens with animals? If we have a dolphin And is it going to be sucked in a turbine? And is it going to end up as dolphin sushi? Some environmental groups were very opposed to tidal turbines, even if it's green energy, because of that. Biologists were a bit more blasé, saying, well, if a dolphin is stupid enough to put its head in the blades, it's going to die soon anyway. So what we did, we were commissioned by the government to design some instruments to map out what's going on. And to cut a long story short, I can reassure you, no dolphins were harmed, no other animals were harmed. So this image at the bottom shows us where the turbine is, and we put a 1-ton platform at the bottom of the sea, 50 meters down, and we have one sonar that images the whole water column there. We can see targets, so that's animals usually, moving around. We can spy on them. We take images 8 times a second for maybe 2 weeks at a time or more, and we can see anything moving within these 50 meters. And then we have other types of sonars that use different frequencies. They create images like these, and we can recognize the types of animals. For example, we can recognize when we have a fish show, but we can see what kind of fish it is. We can also see the tracks of animals like seabirds diving there, because very often all these devices on the seabed are forbidden to local activities, so they're havens for biodiversity. The fish very quickly realize you have nice moving water and no fishermen around, so they congregate there, which means the seabirds and the marine mammals congregate where the fish is. So we're able to actually map out and check that no animals are actually harmed by all these devices, so that this green energy really is green. Another type of use that we have for acoustics is listening to the noise of climate change. And I've been doing that around the North Pole, in the Arctic. We have complex ecosystems with marine mammals, fish. We have different types of plankton, but we have ice as well. The image on the right was taken by my colleague, Professor Jaroslav Tedgowski at the University of Gdansk, during some expeditions where we were analyzing the data together. This shows a glacier. This one is terminating by the sea. It is 50 meters high, so it's a small picture, but a very big glacier. It's extending underwater. And even if the water is very quiet, it is actually making a lot of noise from all the ice melting. Very often, this ice is full of bubbles. And what it's going to do is like a glass of fizzy ice with an ice cube. You're going to hear all the bubbles coming out as they melt. When we listen to different frequency bands, we can see, for example, what is coming from the ice, from the weather, from ships, from marine animals, and we can map out what it tells us about the landscapes or the soundscapes in this case. So these fragile ecosystems are affected by climate change. We can check human activities like shipping noise, and we can try to minimize the impacts of our own activities and understand how it's going to be affected by climate change. We can also use multi-aspect sonars. So when we have dolphins, for example, we have eavesdropping dolphins. One dolphin is actually vocalizing, finding out where the fish are from the echoes, but very often some of the fish know that a dolphin is sending acoustic waves trying to get them, so they move away. And other dolphins are actually listening, and they just catch these fish based on the echoes there. We use exactly the same technique underwater. We have done, for example, lab experiments at the University of Bath, and we have looked at different types of targets buried in different types of seabeds. And we've used that at sea, for example, in the Stockholm archipelago. And most of the time, most of the acoustic energy that we send is going to propagate away. It has a lot of information about the makeup of a target, even if it's buried in the seabed. So by listening from elsewhere, we can hear more. We can detect small objects, find out what they're made of and what is inside. And we use that, for example, to look at toxic waste buried at sea, telling cleanup efforts which places require urgent information because, for example, everything is corroding, and which places can stay without being cleaned for a longer time. So we can use that for all sorts of purposes. We have used this same idea of looking from different directions with radars, that's like sonars. We send waves and we look at the echoes. And in that case, we have decided to look in space at the big problem of space debris. Just 10 days ago, we had a fragment of a rocket that fell back to Earth. Luckily, it fell in the ocean. But there are lots of debris flying off in space. This map is a current map. It just maps everything bigger than 10 centimeters. But there are many more debris smaller than 10 centimeters at all sorts of orbits. At some point, it's going to create what is the Kessler syndrome, when space will be so crowded, anything we send in space is going to bump or crash onto these debris. So our technique is to use different types of satellites, nanosatellites with radar, to image debris clouds and map out which places are the most dangerous, which places have the most debris that we can clean up, and warn, for example, other satellites and say, you have to move the International Space Station by this distance or sideways to avoid this big debris coming your way. And we can use that for planetary exploration. For example, looking at rings around other planets and moving into very cluttered environments. So the same techniques of waves, sonar waves or radar waves can be used from the deep sea to outer space. And I will finish there by saying that the world has changed a lot over the last 10,000 years. This slide, for example, contrasts what happened on land from the time of mammoths to now and the near future, the next 100 years, and what is happening or has happened under the sea there. So what we can do is use physics to explore the world around us, make sense of this diversity. Remember, we're not only on a small planet, we're here, just in one galaxy among many. So sound is essential to understand the present and future of the oceans, and physics is essential to measure, adapt, and protect the environment around us. So everybody needs a physicist. Thank you.
Thank you very much, Philippe. That was really interesting indeed, and it just shows us how important we need to adapt, and we need to use new technology and new work such as yours to evolve and to evolve to the ecosystem around us. It can't be just us, but also the earth and the ecosystems. Now that we've finished with the two talks, I'd like to invite our both speakers on screen and start with the Q&A session. Please, if you haven't done, welcome back.
Hello.
If you haven't asked your questions or your comments, please feel free to drop them in the comments section, and yeah, we can discuss them. So the first question is from Michael Barrett, and the question is, do we know if two black holes have ever joined together?
So we actually do know this. So I guess kind of stepping back a bit. So I talked a bit about those galaxies, and they're all having these supermassive black hole in their centers. And actually through the history of the universe, those galaxies are not staying isolated. So at times they will basically start to what we call merge. So they'll start to collide and then form one bigger galaxy. And that happens quite frequently in the history of galaxies. And in that case, of course, you'll then have a new galaxy, which in the beginning will have two supermassive black holes. And we do believe, or we're kind of very strongly convinced that they will merge. We have not directly observed the event of the merging, but we know that they must merge after the galaxies have merged. So in the future, hopefully maybe 10, 20 years, we might be able to observe that through gravitational waves, but currently we don't have this technology. And then, of course, you might have heard from LIGO, the gravitational wave detector. So that has previously looked at smaller black holes. So I talked about the supermassive black holes, but we also have black holes that are only a few solar masses. And now we actually directly have observed these basically mergers of two black holes to form a bigger black hole. So we know that this has happened and is happening quite a lot.
Yeah, that's great. Thank you. Thank you, Carolin. I think that answers the question. And now moving on to the second one from Greg. Has the eavesdropping sonar been used to find aircraft crash in the ocean?
That's a very good question. When we look for aircraft that crash in the ocean, these aircraft usually have a beacon. So they have a black box and they have a pinger that sends sound that we can listen to. In recent aircraft crashes, people first look for these sounds to home in, so to triangulate and find out where it's coming from at the bottom of the ocean. Sometimes it doesn't work because the water is too deep or because the signal is blocked by mountain ranges. In that case, we use normal sonars mapping the seabed. So we don't need to use eavesdropping sonar. In that case, just normal run-of-the-mill sonars you can buy in the shops or in the internet would work perfectly.
Yeah, that's great. That's great, Philippe. Well done on that work as well. Moving on to the next question. We have from Richard, which came first, the galaxy or the supermassive black hole at its center?
That is a great question because we don't actually know, and it's a really exciting question. So I talked a lot about kind of the galaxies that we see nowadays, but of course, both the galaxy and the black hole has to have formed somewhere at the very beginning of the universe. And it's actually very hard to figure out how exactly these first sort of seeds for the black holes formed. So there's a few different processes, and we kind of know that even a few 100 million years after the beginning of the universe, we had supermassive black holes. So it looks like both of them formed quite early on, but we're still trying to figure out how those first black holes basically got created. But basically, they formed in unison very, very early on. So the question is just like, who was growing first?
I imagine there's some work around it as well. There's been some work.
Yeah, I think so. This is very exciting because basically you're trying to look at the very beginning of the universe and trying to figure out what happened there. And of course, that means that you have to look very far into the past, which means you have to look very far away. And that means that basically all the emission starts to be extremely faint. So that kind of work, trying to understand the beginning of the universe, is very, very challenging because the objects are just extremely faint. And then there's also the problem that at the very beginning, the universe was not really see-through, which makes it even more challenging.
Definitely.
So we're figuring it out, Estia.
Well, good luck on that. I'm pretty sure that everyone will appreciate if you do.
Yeah, we will, I'm sure.
Moving on to the next question now. We have from Riz. Do we know how close are we to having too much debris in space?
Yes, we can have an idea. So the Kessler syndrome was proposed by Kessler and colleagues back in 1973, 1974, and is based on the increasing density of all these debris. So as we have more and more debris, some of them are out of control. They're going to bump into each other and create more debris. We have seen that with some satellites bumping into each other. As we have constellations of thousands of satellites now being launched into space, some of them are going to be bound to collide with others. For example, one of the rockets going out to the space station a few weeks ago was within 50 meters of one of these smaller satellites. So luckily they avoided a collision, but we're getting dangerously close and increasingly close to having too much debris in space, which is why we need to do the space cleanup first. And we need to know where all these debris are as well.
Yeah, so we should stop sending some more satellites now, right?
Not only that, it's very often satellite operators are very responsible. Mm-hmm. They make sure that they send things on orbits which are not used or where they don't have any risk of colliding. And they have deorbiting strategies. For example, they send things back to burn into the atmosphere at the end of their life. Okay. Some of the older satellites don't. They're just left out there and decay and are out of control. And sometimes accidents do happen. Satellites do not respond to control, and they just come back down crashing and hopefully not colliding into anything on the way down.
I see. Thank you for that. Next question, I think it's from Paul. And I thought black holes at a very low temperature.
So black holes are a bit curious objects because the only property they really have is actually the mass, the spin, which is basically how fast it turns in a way, and any charge. So they don't really have a temperature themselves. I think that the confusing bit about this whole black hole accretion disk is that the properties of the black hole are that it's extremely massive, extremely compact. So what is hot here is when I talk about this hot accretion disk, that's not the black hole itself. That's the material as it's like falling into the black hole. So that is what has this very, very high temperature. The black hole itself does not really have a temperature. And it's that accretion disk, that material comes in that heats up to very high temperature. So that's very, very hot. The black hole itself is not hot.
Okay, thank you for that.
That answers the question, but a little bit hard to check nowadays. But
Thank you. The next question will be from Jenny. And the question is, how do we plan to clean up space? Philippe?
Okay, and I see there is another question coming. How difficult is it to clear off space debris? And is there a reason we can't scoop it up or push it further out into space? It's a bit like cleaning your house. Either you get rid of the dust or you put it under a carpet and it's going to come back at some point. So pushing it further into space, we're going to bump into it at some point. Scooping it up, that's indeed the best option. You're right there. But it's very difficult to do. First, because even if space debris is sometimes quite big, it's going to move around at very high speeds of kilometers per second, several kilometers per second. And sometimes it's not that dense. So it's going to be a few debris within a few cubic kilometers. So that's still going to be dangerous when you have even small bits of dust flying at kilometers per second can make holes, for example, in the windows of a space station. So we have to first go to the debris. So it's a matter of how much energy, how much power we have, then how we can collect it. So there are programs, for example, using a harpoon or using magnets. But mostly it's finding out where the most dangerous debris is. So it's difficult to scoop it up because it would be like scooping the plastic out of the sea. We know it's bad. We know where we have concentrations, but it's still going to be difficult to scoop it up all there, even if we really want to.
Okay, that's great, Philippe. Yeah, thank you. The next question is from Reese. Why does energy radiate in form of a disk?
So the reason you have the disk structure itself is basically because any infalling material will have something called angular momentum. So some way of thinking about this is that there's a black hole in the center of a galaxy and you're basically throwing things at it. And anything you throw kind of off center would basically start spinning around a black hole. So it basically has some kind of a spin with respect to the black hole. So unless you hit it at a very specific angle, anything falling into the black hole will basically have a sense of spin, and it will retain that. So this is why it forms this kind of disky structure. Mm-hmm. It's because of the way it has been accreted. And then it will start to form this disk. And then the radiation is purely due to the fact that basically through this kind of change of the gravitational potential energy, this material is heated up. And it's heated up because it's basically the different orbits are basically rubbing against each other and kind of just warming up the whole disk. And this is what's radiating. It's just radiating because it's hot. And it's a disk because the incoming material will have had some kind of a sense of rotation around the black hole. So this is why it forms a disky structure.
Okay, yeah, I think that answers it pretty well. Thank you, Carolin. The next question we have is from Ben, and how much does man-made sound from shipping, etc., impact on life in the oceans?
That's a very good question, Ben. Thanks a lot for asking that, because this is exactly the focus of our acoustics research at the moment. When I presented the work in the Arctic, actually, I'm co-chairing a working group at the International Quiet Ocean Experiment, where we try to understand the impacts of noise from all sources, and shipping is a big source of noise. I was talking recently with a colleague who was north of Alaska, and he was listening to whales in a protected area. And in the data he had, he could hear every now and then some regular bangs, very faint, but still there, when nobody should have been doing any seismic exploration there. And he tried to track out where the noise was coming from, and nobody was doing any work there. The noise was actually coming from north of Norway, where they had a license to do seismic exploration. And the sound was traveling all the way across the Arctic, all the way from the north of Norway to Alaska. And it could still be heard there. Seismic noise is, of course, much larger, but the noise from ships can be heard tens of kilometers away. And it's like living next to a motorway. So it's fine if it's every now and then. If it's day and night, it's going to be really worrying. If it's too loud, at some point, you're going to think about moving out, which is what the animals do. So they tend to directly feel the impact of shipping. Shipping, as well, is increasing over all the oceans for economic reasons. So we have to be careful about where it happens. And this is where we do work with British standards, for example, and the ISO, the International Standards Organization. What is the best way to measure ships, the noise they make, and find out the impact they have on the oceans? So my colleagues around Vancouver Island have, for example, put hydrophones in the sound north of Vancouver Harbour, and they monitor the noise from ships. It's a voluntary thing, but usually ship owners are very happy to know how noisy their ships are, because all the energy that goes in the oceans is energy that they don't need to create. So that's going to save them money in the long term. And then they tell them what speed they can go at based on their acoustic impacts. And then they have other hydrophones that tell them where they have whales around. So they say, oh, we have a pod of whales 5 kilometers this way, go down to that speed. Or there is no whale around, you can go faster. So it's a win-win situation, both for the whales and for the shipping industry, to be able to reduce the noise they make.
Thank you, Philippe. That's really interesting, and it's important to do as well. The discussion is really good, but I'm afraid we're running out of time. So I'd like to thank you everyone for participating, for dropping in your questions as well to our speakers. I'd like to thank you again, to thank our speakers for such interesting talks. And I'd like to finish by thanking everyone in the backstage, namely Catherine and Luca, who helped preparing this live show. Luca, who is the producer, Yvonne, the Master of Commons, and at last but not at least, Reese and Lewis, who are the coordinators, both coordinators, and have helped a lot preparing this. So thank you, everyone. I hope you enjoyed as much as I did, and see you soon. Don't forget to take your pint of knowledge every day. Thank you.